Okay. Hi, my name's Eric.
Hi, Eric.
Wow, that's pretty good for 9 in the morning. Yeah, let's do this. All right, so the name of my talk, wow, that's a great start, is why is Python so fast? But I really prefer the alternative title, which is Welcome to the Spaghetti Factory. So this talk is going to be a little bit of down the rabbit hole, and we're hopefully going to have a little fun, and hopefully by the end of this talk, you will understand why this is the alternative title. It's because Python gets a little ridiculous when you go down the rabbit hole. So, surprise, this talk, this is me. Sorry, I completely forgot this. Hi, my name's Eric. I'm an engineer and on the founding team of a startup called Yhat. We have products that try to increase the productivity of enterprise data science teams. So yeah, surprise, this talk isn't really about speed. It's about data science, right? So if you haven't heard, Python and data really go well together. So Python is becoming a very, very, very popular language to do data analysis. And one of the best ways maybe I could prove this is just look at PyGotham, right? So right before I came here and right as I was making these slides, I decided to just go through the list of talks at PyGotham and see which ones were about data science. And I got that, right? So as you can see, a lot of, and maybe this is a broad sort of definition of data science, but a lot of talks are about doing analysis with Python, right? And you can sort of see why this is. There are a lot of awesome tools to do data science in Python. This talk is not explicitly about it, so it's not super important that you know what these are. But one example might be scikit-learn, which is a machine learning library in Python. It's really cool because you can do from scikit-learn import this awesome, statistical modeling software, and you can use it very easily. StatsModel is a good one for econometrics and time series data, and pandas is awesome for looking at data and working with it in tabular form. So this is a little weird. And it's weird because when you think of scientific computing, when you think of doing analysis with computer languages, the ones that I sort of learned in college and the ones that are very prevalent are languages that started as scientific programming languages, right? So you have here, and I really regret if any of you have had to use the two on the left, which are Mathematica and MATLAB. But we also have R, and I put Julia up there because I really, really hope it takes off. But the thing about these programming languages, and you don't really have to know what they are, but they're popular and they're also built from the ground up to do scientific computing. And Python just absolutely is not this way. It starts as more of a general programming language and somehow gets really, really popular in the space of doing data science. So that's weird to me because when I think of doing statistics and I think of doing analysis on data, I think of lots and lots and lots of computation, right? So when you're trying to do a classification or you're trying to do some sort of regression analysis, you're actually just doing a lot of math, right? And surprise, Python is really slow. So I know my talk is Python is fast, but we're going to start with this assumption that actually, no, Python is very slow. And let's just think about a very simple example, right? So we have a list, right? And for this purposes, since we're being mathy, I'll call this like a vector or something, right? So it's 0, 1, 2, 3, 4. And all I want to do is add 1 to every element of that list, right? So this is awesome in Python. We can display this very elegantly, very cleanly, and we can just do this little for thing. I actually don't know what the proper name of this is. I think it's a list compression. Is that?
Comprehension.
Perfect. I like this crowd. So we can add 1, right, and get this transformation, right? So this is a really common thing to do in math, right? We just want to transform one array into another array. So I decided to time this and wrote this little script. And if you see at the top left, I don't know if you can see it, but it's instead of an array of 5, we're going to use an array of 10 million, okay? And we're going to just add 1 to it, and we're going to do that 100 times. And that's the important part right there, right? So I just want to time it to see exactly how long this is going to take. and it takes about 100 seconds, right? So that's all right. To give you a little context, and you might want to look away, this is C code, okay? So this is ugly. I don't like programming in C, but I wrote this just to give you an idea of how fast other programming languages are. It does the exact same thing. You don't need to worry about exactly what it's doing, but that's the thing we care about. And when we look at it, 2.5 seconds, right? So Python is just inherently slow, and yet we're using it for data science. This is sort of this weird paradigm, right? And why it's slow is way too much to get into right now. I suggest this really awesome blog post called Why Python is Slow by this guy named Jake Vanderplas, he's an astronomer that uses Python, right? And we just think about adding two numbers. So in C, this would be like one operation. But in Python, we have to check x. That's good. In Python, we have to check x, notice that it's an integer, check y, notice that it's an integer, get the function and compile it for adding two integers, and then we add two integers, right? So that's a lot more than just 1 + 1 = 2. And the biggest way that we get around this is this particular library called numpy. And numpy is short for numerical Python, right? And rather than just talk about it, I figured I'd actually show it to you guys. So we're going to switch. I hope everyone's OK with that. So dot product fun. There's a little math in this presentation, by the way. So I apologize in advance. So as we can actually see, Python is pretty fast, right? So in this, I take some machine learning algorithm called elastic net, and I take it in, and I'm going to train it, right? And what exactly happens here isn't important, but you look that the matrix I'm making is about 100,000 by 1,000 matrix, and I'm going to do some computations on it, right? And this is pretty fast in Python, right? So this would be counter to the thing that we showed earlier. It actually only takes 3.1 seconds, right? And your computer may vary. So this is me profiling that code. And yeah, you should not be able to get much out of this. I really hope. But this is the one thing that you probably want to care about. So this is a matrix multiplication. And we know that it's called 3 times up here. If you can't see, just trust me. And the amount of time it takes to compute one of those is about 0.3 seconds. So this is this one thing that's actually taking a very, very long time to do, right? So out of our entire 3 seconds, this thing is only called 3 times, and it's taking a huge amount of time to execute, right? So let's look at that and see what's going on there. So just to explain a little bit of math, this is a matrix multiplication. It takes a while. We just want to think very simply about what it does, just so everyone's on the same page. I know it's been a while since I took linear algebra. I don't know about you guys, but so A times B equals C, right? So just to give you an idea of what's happening, to compute C, we care about, like, to compute this value of C, we care about the top row of A and the leftmost column of B. We multiply them, add those resulting multiplications together, and get that. Perfect. You do not need to understand this whatsoever, right? So we can do that again for another value of C. And eventually, we do some black magic, and we get another matrix, right? Importantly, we're taking two matrices, and we're combining them in some funny way, and we're getting another one. And this so happens to be kind of important we do this a lot when we do statistical learning. So let's see how fast we can make Python go, right? So what I'm going to do here is I'm going to write a matrix multiplication and see how fast I can make it, right? So just a little helper function here. This is a function that just gives me a random matrix, okay? So I have 3 by 5 right here. You see the result. It looks cool. It's Python lists. And I'm just going to make 2 arrays, or 2 matrices, A and B, and they're going to be about 1,000 by 100, right? So that's not important about exactly what size. They're big, okay? So this is programmatically what a matrix multiplication looks like. Again, this code isn't important that you understand it, but we're having some fun here, right? So this will actually do the exact same thing as numpy. And when I profile a code, it takes about 17 seconds, right? So that's a lot slower than the 3 seconds that we saw earlier. So how can we speed this process up? Well, I'm going to use this thing called Python, right? So Python is an awesome language because it's very dynamic, right? I can sort of just have an object, and I don't care about what it is, right? I can throw that object around. It could be a number in one point. It can be a string in another, and that's OK. But Python code looks like this. And this is code that will actually run as Python code, but compiles down to C. So I have this, like these integers, right? Int 1j, or ij, k. And this looks very un-Pythonic, right? But just by giving the computer some hints of saying, hey, I know I have this, object, I. I'm just going to warn you ahead of time that it's an integer, right? So we can do that. We can wrap some stuff around it, compile it down, and eventually we can speed it up to that. So again, it's not important that you understand what's happening, but just notice that by introducing this thing we call Python, we can suddenly speed it up a lot, right? So we've reduced the time by about 2 orders of magnitude. Cool. So I'm just going to make it a little bigger, the matrix is a little bigger, so my benchmarking helps out. So the new time to beat is now that. So that's all that slide is. So the way NumPy works is that it takes these lists, these very abstract things, and actually puts them into memory, right, as one block in memory. And actually, we can do this little trick, because the way we would think normally of like a matrix is this, right? So this is like a very mathy thing. But this is actually just how the computer looks at it in memory, right? So it's just a block of memory with 1, 2, 3, and so on. And it actually matters which way we iterate through that list, right? So if I go 1, 3, 2, 4, I'm actually skipping back and forth. So that's just a little fun observation. But what would happen if instead of going 1, 3, 2, 4, I just went 1, 2, 3, 4? I'd just be going one point at a time in memory, right? So I'm going to write the code that does that. It's a little nuanced about why it does it. All I've actually done is switch these 2 for loops, right? But in the end, we can speed it up even faster. So we're getting faster, guys. It's good. Can we go even faster? So this is the point where I might lose a few of you, and that's the point. So just hang in there. This is Fortran code. Fortran is a programming language developed by one of my former employers, IBM. And it's been around since about 1950, right? Fortran and C have been the gold standard of speed, right? So this does that exact same thing, same as the other programs that I was writing. And we're going to see how fast this is, right? And if this feels ridiculous, good. It should feel ridiculous, right? We've gone from this beautiful, awesome Python to this, which is ugly, ugly as all hell. All right, so let's see. OK, so it would appear that we've sort of hit diminishing returns, right? I busted out some Python. I've optimized my matrix multiplication. I've written Fortran. And it looks like we aren't getting much faster. So how does NumPy compare, right? How does that matrix multiplication in NumPy look like? Way faster. So either I'm a really horrible programmer or something's happening there that we just aren't understanding, right? So NumPy, numerical Python, is going really, really fast. And why is that? So yeah, why is that? So to answer this question, I decided let's go on over to GitHub, right? NumPy is an open source project. We'll go check out the source code. So I got to this. I was like deep in the code of NumPy. I found this file called numeric.py. And right around there, there's no way any of you can read that, but it says from _.BLAS import dot. Right? And we're all Python programmers, so we know that if I have from something import something, there has to be either a directory or a file there, right? So I say from file A import whatever. So unfortunately, the source code wasn't on GitHub for that file. it doesn't exist, right? It's sort of made when you install it on your computer. Luckily, it is on my computer. So bottom left, whoa. Bottom left, way down here, is this thing called _.blas.so, right? And we're gonna, so I decided, let's open up the file and see what's happening there, right? And I got that, which makes me sad. So what we've actually hit is way down in the rabbit hole, and it's just this weird compiled code, right? And the only hint that I could get about what's going on at this point is this little thing. And that's this, if you guys can read that, you have really sharp eyes. But what it says is system library frameworks accelerate.framework, right? So this is where you all notice that I am on a Mac, right? So do some Googling around, and you find this, right? Which is a framework that's actually built in to my computer. And if you see down here, accelerate.framework, right? So that's the thing. We're really close to actually figuring out what's happening. And this is kind of the point where I just have to spill the beans. So what's happening is that numpy is actually calling, way down at the low level, this, BLAS, right? So what BLAS is, it stands for Basic Linear Algebra Subprocesses, right? The reason the Pink Floyd's up there is because it was actually specified in 1973, though the matrix multiplication was added later, and we'll admit that. And what it is people thought, hey, we do this linear algebra a lot. It'd be great if we just had like an API for that, or like a very specific spec for that kind of thing, right? And what came out of this was these basic linear algebra subprocesses. And because Apple knows exactly what CPU types and what metal their operating system is running on, right? Apple only ships OS X on one type of computer. They can then optimize it in incredible ways that I am not qualified to speak on, right? So what's happening? We're starting from this thing that's Python, right? Beautiful, lovely Python. We're all here for that, right? It's calling a C extension called _.blas, which in turn is then calling this thing that's baked into my operating system, right? So what we see is that Python is being used as this duct tape, right? Python is the duct tape between Fortran code. In this case, it's C code, but it's the duct tape between all these wonderful processes, right? And this turns out to be not novel, right? So I'm just going to read this quote, if everyone's OK with that. Using Python, better applications can be developed because different kinds of programmers can work together on a project. For example, when building a scientific application, C and C++ programmers can implement efficient numerical algorithms, while scientists on the same project can write Python programs that test and use those algorithms. And this quote is, of course, by the inventor of Python. And when I say it's not novel, it's because it's from 1998. Right? So when we see something like numpy, it is the wonderful amalgamation of this ideology that Python is extendable. Right? When Python is created, there are easy ways of calling Fortran code, of calling C code. And that, sticking to that ideology, has given us the ability to do scientific programming in Python, and has given us the ability to do that. So thanks.
What was that?
This is all the talks at PyGotham that use scientific computing. Thanks. Some interesting things. Yeah. Questions, cool.
So, I mean, I guess the next logical thing is we have Ubuntu on this.
Yeah.
So, I guess there's the equivalence for what we see that file in.
Yeah, so again, this is like way down at lower levels. You have BLAS on Ubuntu. You should have Atlas, so you should Google that and figure out what that is. But yeah.
So in terms of finding
Sorry, yeah.
In terms of just one last thing, in terms of how you got to find? I just basically just did like a find and just search for .blast.
Oh man, yeah, that was the result of a lot of like, let me go look at this source file, but
Okay.
just yeah, not to me.
So to that point, .blast is compiled by numpy. You build it.
Okay.
It calls into Atlas, like that called BLAS.
Okay.
You can build all of those for your machine.
Yeah.
Atlas will do some benchmarking during the compile process.
Yeah.
Okay.
And if I may, just so we can like have other questions that aren't like super technical, yeah. But so if you guys want to talk about that after, I'd be happy to.
Okay.
Yeah.
Before you did the multiplication in numpy,
Yeah.
when you were using like the Cyphon,
Yeah.
did you try representing some of the arrays with like Fortran style pointers, and like one of them with Fortran style pointers and the other with C style pointer?
No, I didn't, but I mean, I could. Yeah, that would be cool. And that has to do with like the way they're, if you're going row by or column. Is that what you're talking about? Okay, yeah, I could have. Yeah. Any other questions around here?
So you're gonna post the slides?
Well, yeah, it's weird because I have this IPython notebook that is like in the middle, which is kind of important. So I'll figure out how to do that, and then I'll post the slide. Yeah, you should all follow me on Twitter, which is that's a plug.
Oh, can you
Yeah.
go back to that matrix slide?
Which one?
Just for a second. The one that you said, no, it doesn't matter.
Which?
The dot product slide.
It had A and B.
Oh, those ones. Those are this, and I'm getting kicked out, which I know is why you're here.
I'm actually going to get your slides.
Oh, yeah. So I have this weird thing in the middle, so maybe we can talk about how we want to do that. But yeah. Any other questions that aren't about slides and stuff? Awesome. Yeah. Well, thanks.